In this session, we're going to explore sequences. A sequence is a function whose domain is the set of natural numbers, which means that what goes into the function is the set 1, 2, 3. They're just positive whole numbers. It's kind of a different way to look at function notation. The nth term of a sequence, it seems kind of weird, but it's denoted a sub n. So we can say the first term is a sub 1, the second term is a sub 2, the third term is a sub 3, and then some generic term down the road is going to be a sub n. Now n could be, 10 or 100 or something, any whole number. And I think the best way to learn about a sequence is to just dive right in. Our first example is to find the first 5 terms and the nth term of this particular sequence. A sub n is equal to n squared plus 1. Like I said, it's just a different way to look at function notation. In function notation, we might see this as f of x is equal to x squared plus 1. And you're used to xy tables, where x is your set of inputs, and y is your set of outputs. And the only difference is in a sequence, the inputs start with 1 and increase by 1 each time. They're just positive integers. So the first 5 terms, that means we're supposed to find a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, and then and the 10th term. So that means also a sub 10. If it seems like this is going to be easy, you're right. A sub 1 is going to be 1 squared plus 1, which is 2. A sub 2 is going to be 2 squared plus 1, which is 5. A sub 3, 3 squared plus 1, which is 10. A sub 4, 4 squared plus... it's that easy. It really is. What you're doing here is you're just getting used to the notation, okay? A sub 5 is 5 squared plus 1, which is 26. And then a sub 10 is going to be, you guessed it, 10 squared plus 1, so 101. The way we would write down the terms is we would say, the terms are 2, 5, 10, 17, 26, and then we can say ... This continues on. Somewhere down the road you have the number 101, right? That's the 10th term. But here are the first 5 terms and the 10th term. Now let's find the first 5 terms and the 10th term of this next sequence, which is a sub n is equal to negative 1 to the n over n plus 1 times n plus 2. Why don't you pause this and try it on your own? When we write down that a sub n is equal to something, that n is called a subscript. And so what we could say is that the subscript becomes the input value for these terms. And as you can see, for a sub 1, everywhere I saw an n, I've replaced it with the number 1. Likewise, 2, 3, 4, etc. So a sub 1 is going to be negative 1 to the 1, so that just means that it's a negative number, right? Negative 1 divided by 2 times 3, so 6. A sub 2 is going to have negative 1 squared. That's a positive 1 in the numerator. So that's what that negative 1 to the n does. It makes it so that terms are positive or negative. And then in the denominator we have 2 plus 1 times 2 plus 2, 3 times 4. That gives me 12. A sub 3 is negative 1 cubed in the numerator, so that's a negative 1. And then in the denominator, 3 plus 1 times 3 plus 2, that's 4 times 5, giving us 20. So a sub 4 is going to be 1 over 5 times 6 is 30. A sub 5 is going to be negative 1 over 6 times 7, which is 42. And then finally, a sub 10 is negative 1 to the 10th, so positive 1, divided by 10 plus 1 times 10 plus 2. 11 times 12 is 132. So we might answer this question by saying the answer is negative 1/6, 1/12, negative 1/20th. And when we're writing out terms of a sequence, we separate them by commas. 1/30th, negative 1/42, and then dot, dot, dot. That's how we can write down the sequence. And then we can say that, and by the way, a sub 10 is equal to 1/132. And this would be a sufficient way to write the answer here. Well, okay, technically speaking, we were asked for the first 5 terms, so I'm going to erase the comma and the dot, dot, dot from the first row there, and this would actually be the answer. For our next example, you're coming at it from the other side. Here we have a sequence, negative 1/3, 1/9, negative 1/27, 1/81. And the dot, dot, dot just means the sequence continues on forever and ever. There are an infinite number of terms. And when we're asked to find the nth term, what we're basically asked for is the formula. And the formula is going to look like a sub n is equal to. I want to know what the rule is to get any particular term. A way I have found that is useful for finding this is to write down the terms with the numbers that they're associated with. That is, a sub 1 is the first term, and that actual term is negative 1/3. A sub 2 is 1/9. A sub 3 is negative 1/27, and a sub 4 is equal to 1/81. Now I've kind of separated them out, and I see that we have this plus minus thing, right? This alternating sign thing going on. And we saw in the previous example how to deal with that. That means we're going to have a negative 1 to some power. And in the first term, I see that that is negative, and the subscript, or the index, that's another way to refer to that, the index, is odd. And a negative 1 to an odd power will give me a negative result. The denominator, I notice, is 3, and I'm just going to leave that as it is for now. For the second term, we have a positive entry, right? It's 1/9. So it makes sense that that might be negative 1 with an even exponent, so 2 seems good to me. And the denominator is going to be, well, it's 9, and seems to me that 9 could be written as 3 squared. We'll just let that sit again. The third term, negative 1/27. Well, we've got that odd numerator. We might be tempted to write down it's negative 1 to the first power, but remember that whatever's changing has to change in the same way each time. In other words, for the first term I have an exponent on that negative 1 of 1. The second term I wrote 2, so it should make sense for the third term. I want to write down a 3. You see, this is kind of like, a counting thing, really. In the denominator, the denominator is 27, and if we're paying attention, we might realize, hey, 27 is 3 cubed. Now, this is pattern recognition. What pattern do I see? For a1, when the subscript is 1, the exponent in the numerator on negative 1 is 1, and the exponent on the denominator, 3, could be written as 1. That seems to work. For a sub 2, where the index or the subscript is 2, we wrote down that the exponent on negative 1 is 2, and in the denominator, the exponent on 3 was also 2. That matches. That's really important. For a sub 3, we're looking at negative 1 cubed and 3 cubed. So I'm going to make a wild guess and say that for a sub 4, I'm going to have negative 1 to the 4th, and then in the denominator, 3 to the 4th. Now that's technically a guess. Let me see if it works out the way it's supposed to. If I have negative 1 to the 4th power in the numerator and 3 to the 4th power in the denominator, is that result really 1/81? The answer is yes. And so now I can write down that the nth term, a sub n, is going to be negative 1 to the n divided by 3 to the n. We could leave it at that, or if you really wanted to, you could combine these two and say that a sub n is negative 1/3 to the n, because those exponents agree. I'd take either one of these as the answer, and this really is just pattern recognition. It's kind of a fun little game. It's kind of a pain sometimes too. For our next example, we're asked to find the nth term of the sequence 1, 4, 7, 10, ... In other words, find the formula. I'm going to do the same thing I did last time. A sub 1 is equal to 1, a sub 2 is equal to 4, a sub 3 is equal to 7, and a sub 4 is equal to 10. And then we're going to see how we can express these with the with n as an input variable. How do I get from 1 to 4? Looks like I could add 3. Is that a pattern that could continue? From 4 to 7 I would add 3, and then from 7 to 10 I would add 3. Okay, now I have a pattern of adding 3 each time. So 4 is equal to 1 plus 3. 7 is 1 plus 3, that 4 plus 3. And then 10 is 1 plus 3 plus 3 plus 3. If this feels very different than the last one, it's because it is. It's pattern recognition, and it's up to us to figure out what the pattern is. Well, the third term, a sub 3, I could write this as 1 plus 2 times 3. The fourth term, a sub 4, which is 10, I could write it as 1 plus 3 times 3. And trying to write it like that, let's see if we can do with a sub 2, which was 4. We wrote it down as 1 plus 3. Maybe I can write it down as something times 3. It would be 1 plus 1 times 3, wouldn't it? And then I'm seeing a pattern emerge. We have 1 plus 1 times 3, 1 plus 2 times 3, 1 plus 3 times 3. For the first term, we could write that down as 1 plus 0 times 3. Okay, now I need to start matching things up with the indices. That's plural for index. A sub 2 was 1 plus 1 times 3. A sub 3 was 1 plus 2 times 3. And a sub 4 was 1 plus 3 times 3. Seems like each time I have a multiple of 3, the multiple that I have is 1 less than the index or the subscript. That works for a sub 1 as well. It's 0 times 3. So now I want to try to write this down in such a way where I'm incorporating each of these indices, right? Each of these subscripts. So for a sub 1, how can I write down 0 using a 1? How about 1 minus 1 times 3? For a sub 2, 1 plus 2 minus 1 times 3. For a sub 3, 1 plus 3 minus 1 times 3. And in that way, I'm able to incorporate a sub 1, 1 minus 1 times 3, plus 1, of course. A sub 2, 1 plus 2 minus 1 times 3. A sub 3, 1 plus 3 minus 1 times 3. So, does it work out that a sub 4 is equal to 1 plus 4 minus 1 times 3? Turns out it does. Using this as our pattern, we can write down that a sub n is going to be 1 plus n minus 1 times 3. Looks like we could simplify this as a matter of fact. Suppose I distributed the 3 there. So this turns out to be 1 plus 3n minus 3. After I simplify, we could say a sub n is equal to 3n minus 2. We might want to verify that this formula is correct. So a sub 2, let's say, 3 times 2 minus 2, does that work? 6 minus 2 is equal to 4. That matches the term that we had. Maybe we double check that a sub 3 works out, and then we'll call it a day on this one. A sub 3, according to our formula that we have, would be 3 times 3 minus 2, and so 9 minus 2, which is 7, that 7 matches up to what it's supposed to. Now I'm confident saying that a sub n is equal to 3 times n minus 2. For our next example, same instructions. Find the nth term, which is find the formula. And our sequence is 1, 1/2, 3, 1/4, 5, 1/6, 7, 1/8. Oh, how weird. A sub 1 is 1. A sub 2 is 1/2. A sub 3 is 3. A sub 4 is 1/4. The rest of the pattern is the same, so I'm not going to bother to write all that down. How can I deal with this? Half of 1 is 1/2, so that's how I might get from A1 to A2, but from A2 to A3, it's not the same thing. There's no half going on there, so that's kind of weird. The key in this case is to recognize that 1/2 is actually the reciprocal of 2. 1/4 is the reciprocal of 4. 1 is 1 to the first power. 3 is 3 to the first power. In other words, I have exponents that are alternating in sign. 1 to the first power, 2 to the negative 1 power, 3 to the first power, 4 to the negative 1 power. Those exponents are alternating in sign. We may remember how we dealt with alternating signs. When we had something like negative 1 to the n, that gave us alternating signs on our terms. Let's note that if n is odd, then negative 1 to the n is going to be negative. If n is even, then negative 1 to the n is going to be positive. So what I have is positive exponents when the index is odd, which means instead of being negative 1 to the n, or negative 1 to the n, say plus 1. We could write that as minus 1, because what the 1 is doing, right, n plus 1, or if we had n minus 1, is it's changing the nature, even versus odd, of the exponent. Another thing I want to point out is that each time the base that has the exponent that's either 1 or negative 1 matches the index. So a sub 2 has a base of 2, a sub 3 has a base of 3. Likewise, a sub 4 has a base of 4. So what I want to do is write down the base to a negative 1 power, with that negative 1 power being either positive or negative as a result, depending on what the input, what the index is. So I'm writing down 1 to the negative 1, 2 to the negative 1, 3 to the negative 1, and 4 to the negative 1. And remember, negative 1 to the n is going to alternate our signs. But if I want to be offset, that is, with an odd index like a sub 1, I want a positive exponent, then I'm going to have to use the n plus 1 as an exponent there. In other words, I'm going to write this down as a sub 1 is 1, and I'm going to write that down as 1 to the negative 1 to the 1 plus 1. That's 1 to an exponent that's positive. 2 to the negative 1 to the 2 plus 1. That's 2 to an exponent that's negative. That's how I'm going to get a reciprocal there. That works for the 3, a sub 3. It also works for a sub 4. So when I see what matches here, a sub 1 is 1 to the negative 1 to the 1 plus 1. A sub 2 is 2 to the negative 1 to the 2 plus 1. You can see that pattern continues. So I'm going to write down that a sub n is n to the negative 1 to the n plus 1, which is basically alternating reciprocals. This is the game. You have to figure out what the pattern is and then write it down in a general formula.